Hello students. In this video we try to understand what is the effect of addition of non-volatile solute on boiling point of the solvent as well as freezing point of the solvent. Okay. First of all, we know that whenever a non-volatile solute is added into solvent, what we notice is the escaping tendency of liquid molecules will decrease, and if that is the case, vapor pressure of the liquid will decrease. Is it clear, students? Once vapor pressure decreases, then we'll have to heat it to bring it to normal vapor pressure, to its original vapor pressure. Let me repeat. When a non-volatile solute is added to solvent's vapor pressure will decrease. Clear? Now, to make the vapor pressure of the solvent equal to its original vapor pressure, we'll have to heat the solvent containing solute. Clear, students? Therefore, it appears that boiling point of solvent due to the addition of non-volatile solute increases. Clear? In a similar manner, for the similar reason, freezing point of the solvent will also decrease. Both are, that is, increase in boiling point as well as decrease in freezing point, both are occurring due to the decrease in the vapor pressure of the solvent. Now this decrease in the vapor pressure of the solvent occurs because of the added non-volatile solute. Clear, students? Now let us consider what happens to the boiling point of solvent when we add non-volatile solute into the solvent. This effect is known as elevation. It's also called as increase in boiling point. It's also called as increase in boiling point. See, students, let us try to understand. See here, pure liquid has more vapor pressure. More in the sense compared to this one. Liquid, that is pure liquid plus non-volatile solute. This will be solution of this pure liquid only. It will have less vapor pressure. Yes, students, this non-volatile solute decreases the vapor pressure of pure solvent. Therefore, vapor pressure will decrease and boiling point will increase. This we will like to represent in graphical manner. See, students, this is say atmospheric pressure, this is vapor pressure, and this is temperature. Along this axis, vapor pressure variation is noticed, and here temperature. What we notice is this will be the behavior of pure solvent. It means that whenever, see students, whenever temperature is increased, vapor pressure will also increase. Vapor pressure also increases here. As temperature increases, vapor pressure will also increase, and at this particular temperature, say T1, what we notice is vapor pressure of liquid and atmospheric pressure both will become equal. That means here vapor pressure of liquid becomes equal to atmospheric pressure. Clear, students? At this temperature, what we notice is vapor pressure of liquid becomes equal to atmospheric pressure. Therefore, this temperature is called as boiling point, provided the pressure is constant. That means at constant pressure of the surrounding, the temperature at which vapor pressure of liquid becomes equal to atmospheric pressure, that temperature is called as boiling point of the solvent or pure solvent here. Now, what we have noticed is here, whenever a non-volatile solute is added to pure liquid, it will become solution, isn't it? And its vapor pressure compared to pure solvent, what happens? It will decrease. See here, solution's vapor pressure will be less than the solvent's vapor pressure. Therefore, now we represent that. Suppose at this temperature, see here, this is the vapor pressure of pure solvent. This is solvent. This is the vapor pressure of solvent. Now let this be the vapor pressure of solution. Then what we notice? It will increase like this when we heat the temperature, and it will cross this line at this temperature. At this temperature. What we are noticing here? At this temperature, that is T2 temperature, what is noticed is vapor pressure of solution is equalizing its vapor pressure to the atmospheric pressure. That means at this T2 temperature, vapor pressure of solution is becoming equal to atmospheric pressure. That means vapor pressure of solution becomes equal to atmospheric pressure. Therefore, this temperature is called as boiling point of the solution. Yes, students. That means what we are noticing? Initial boiling point was this much. Now, due to the addition of non-volatile solute, boiling point is increased, isn't it? Therefore, this difference is called as delta T. That means here what we notice is T2 is more than T1 and T2 minus, therefore T2 minus T1 is called as delta T. This is called as increase in boiling point. Boiling point is increased from T1 to T2. From 2. This difference is called as increasing the boiling point. Now, experiments indicates that increase in boiling point is directly proportional to molality. Directly proportional to molality of solution. This is very much important, students. That is, this implies that delta T is directly proportional to M. Delta T is directly proportional to M. Now, what we notice is, what we do now here is, we replace the proportionality sign. That means, this we can write it as delta T is equal to some constant K. As it is related to boiling point, therefore we call it as Kb. K related to boiling into M. Clear, students? Now, to define Kb, what is this Kb? To define this Kb, what we have to do is, we will have to put M is equal to 1. To define this Kb, M should be 1. To define this Kb, M should be 1. See, it means that Kb will be equal to delta Tb. Then what does this mean? This means that Kb is the increase in the boiling point of 1 molal solution. I write here, see. Kb is increase in boiling point of 1 molal solution. Is it clear, students? So what is Kb means? It is the increase in the boiling point of 1 molal solution. Okay. Therefore, it is also called as molal elevation constant, and it is also called as ebuloscopic constant. Ebuloscopic constant. Okay. Here, this Kb can be calculated for different liquids by using M T R by 1000 delta H. See, students, here you need to remember this. This is MT square R by delta H into 1000. This is kb. See here, you forget about this square and you will remember this MTR. There is a one of the brand name of one of the food item, MTR masale, isn't it? MTR. Here what you need to remember is MT square R. R is gas constant. M1 is the molar mass of the solvent. 1000 is a constant. T is the temperature, that is boiling point of the solvent, and this is vaporization. This is delta H is enthalpy of vaporization. Okay, this is how we find the value of kb. Now this equation can be further written as this equation can further be written as, see students, delta Tb is equal to kb into, this is molal. It means that molality can be defined as weight of this solute into 1000 divided by molecular weight of this solute into weight of solvent in gram. See students, by knowing the increase in the boiling point of the solution, we can calculate the molecular weight of the non-volatile solute added. And here what we notice is, see here, delta Tb is inversely proportional to molecular weight of the non-volatile solute added. The substance whose molecular weight is more than its effect on the increase in boiling point is less. That can be the conclusion. Clear students? Next, in the next video, we try to attempt the problems based on these equations. Okay.